When a buyer asks, "How much does a custom impeller tool cost, and how long will it take?" the honest answer cannot start with one number. The tool depends on what must be produced, how it will be made, how performance will be verified, and what production volume the tool must support. A quick price without a released requirement is not a quotation, it is an assumption with a currency symbol and a date attached. First, lock the engineering inputs. Define impeller type, diameter and length, blade geometry, hub and shaft interfaces, material and process, target airflow and pressure, operating speed, temperature and chemical environment, noise objective, balance requirement, expected volume and installation envelope. Identify the mating motor, housing, and inlet conditions. Mark which dimensions and performance targets are critical, which may move during DFM, and who has authority to approve a change. Then separate aerodynamic intent from manufacturable construction. A blade shape that works in simulation may create an impossible parting line, trapped steel, weak section, poor filling path, difficult ejection, or unacceptable distortion. DFM asks how the part splits, fills, cools, shrinks, ejects, joins, and balances. The right discussion is not "can you copy this geometry," but which design features carry performance, and which can change to create a stable manufacturing process. Choose the tooling route only after product and volume are understood. A plastic centrifugal wheel, crossflow blade segment, stamped metal disc, cast wheel, or fabricated prototype may require completely different tooling, fixtures, and validation. Material behavior, part size, annual demand, surface and balance requirements, cavity strategy, inserts, joining method, and expected revisions all change the route. Prototype tooling, bridge tooling, and production tooling are different risk and life decisions, not simply three prices for the same object. A useful quotation exposes the cost boundary. Separate design and DFM, flow or structural analysis where required, tool steel and standard components, machining and EDM, heat treatment, surface treatment, fixtures, gauges, trial material, first articles, correction allowance, inspection, balance and performance tests, packaging and transport. State taxes, spare inserts, engineering changes, maintenance and ownership separately. Without these lines, two quotations can look comparable while covering different deliverables. The timeline also needs gates, not one bar. The clock may include requirement clarification, concept and DFM approval, final CAD release, material procurement, machining, assembly, tool trial, first article measurement, correction loops, balance and performance validation, buyer approval, and production ramp. Name the trigger and exit evidence for every stage. Tool build should not start while critical inputs remain open, and mass production timing should not start from the first trial shot. Before cutting steel, review the evidence package. The Longwell design material shown here includes 3D construction, 2D definition, and mold flow style analysis. Those images demonstrate the categories of work, not a guarantee that every project uses the same software or sequence. The release pack should identify the controlled CAD revision, critical dimensions, material, shrinkage assumptions, parting/ejection strategy, analysis findings, interfaces, inspection method, open risks, and signed approval. Plan the first article before the tool is finished. Decide which dimensions will be measured, how warpage and runout will be checked, what material and process settings are allowed, how appearance and assembly will be judged, and which samples go to balance, airflow, pressure, noise, overspeed, or environmental tests. A first shot is learning evidence, not automatic approval. Record deviations and link every correction to a new tool and part revision. The real plastic impeller production line here shows injection equipment, automated handling, fixtures, assembly, and packing. It proves only visible process context. It does not show tool construction and cannot establish cycle time, capacity, yield, or the route for another impeller. Its value is to reveal downstream questions. Can the part be handled without distortion? Are inserts and joints controlled? Can inspection and traceability follow the release design? Dynamic balance is another release gate. The real crossflow impeller footage shows a balancing machine and operator interaction, but no balance grade or pass result is claimed. Define the test setup, support condition, speed, correction method, acceptance criterion, and data record for the exact assembly. If correction changes geometry or mass distribution, reconnect the result to aerodynamic, strength, noise, and tooling decisions. Validation is a loop, not a box checked once. Commercial control continues after acceptance. Record who owns the tool, where it is stored, who may use it, how it is identified, maintained and inspected, which where parts or inserts are stocked, how production and repair history are logged, and what happens when the design changes or the program ends. Define approval for modifications, transfer, duplication and disposal. A low initial tool price can become expensive when ownership, maintenance or change rights are unclear. Custom impeller tooling becomes predictable when requirements, DFM, route, quotation, schedule, first article, validation and ownership are one controlled system. Price and calendar should be outputs of that system, not the starting promise. For a project-specific review, send Longwell the duty point, speed, envelope, interfaces, material preference, environment, quantity forecast, validation needs and ownership expectations. We can return a gated tooling plan with assumptions, evidence, and open risks clearly marked.